Hi class, this is a strange way to do class. We're going to give it a shot and see how it goes. I hope that lessons 1 and 2 went well. I sent you a quiz via email, and if you haven't already, then I need you to answer those questions. There are 5 of them, and get them back to me. Get your answers back to me. Hallie wins the award for getting hers in first. Good job, Hallie. All right, I graded your chapter 11 tests, and thank you for scanning those and sending those to me. The test scores were pretty average. We had A's, B's, and C's. Nobody below a C, so that was good. The grades are already on iGrade. They're posted there so you can see what you got. All right. If you have questions that you want me to address about lessons 1 and 2, please feel free to do so via email. And if a lot of people ask about the same sort of thing, then I can do a little video lesson about any of those things. But we're going to pick up with lesson 3 and see how that goes. Then I will make a separate video for lesson 4. All right, this lesson is about central angles and central arcs. So chapter 12 is all about the circle, and so these are parts of a circle that we're going to be discussing today. My construction tools are at Blackburn, so I'm going to be freehanding my circles. Your circles at home should look much nicer than my circles, but you know, you got to do what you got to do. So today we are going to be discussing, how's that look? It looks like a circle, so that's pretty good. This is the center of the circle, and the first thing we're going to be talking about are semicircles. Since you are all rocket scientists, I'm sure that you know that a semicircle is half a circle. There you go. So a semicircle is either the top half of a circle or the bottom half of the circle, left or right, depending on where it goes. It's cut in half by a diameter. In this case, I have a secant, which is not a word that you know yet, but a secant goes all the way through a circle, and I just dotted it for fun. So anything that is less than 100, this is 180 degrees. The measure of a semicircle is 180 degrees. Anything less than 180 degrees is called a minor arc. So something like this orange line here would be a minor arc. It is less than 180 degrees. If we have an arc that measures more than 180 degrees, say we start at this location and we go past the semicircle over here. Let me give these some names. This will be A, and this will be B. So our minor arc here is called arc AB, and we put a little arc shape over that to designate that we mean arc AB. If we have a major arc like this, we'll say A, and over here we have point C. It's on the circle. It is nice to have a third point in a major arc so that it's clear which way the arc goes. So in this case, I will call this point D, and arc ADC is a major arc. Major arc is greater than a semicircle. It's more than 180 degrees around the circle, and we call this major arc ADC. Some of you are wondering if we can call it arc A or CDA, and yes, in fact, you can, just like we could call this minor arc arc BA. Either of those will work. All right, so that's semicircle, minor arc, and major arc. In a circle, we can measure angles. I know you were waiting for angles to come, and so now they are here, and you don't have to wait any longer. All right, so in this case, I'm going to draw 2 radii, and you know that all radii of a circle are equal. And I'm going to draw, we'll call this circle O. I'm going to draw radius OB and radius OA. This angle here at O is called a central angle. Central angle. A central angle has its vertex at the center of the circle. That's how it got it. That's how it got its name. Pretty clever, huh? So this central angle is, how big would you guess this central angle is? It's less than 90 degrees, but not a lot. Let's say it's 85 degrees. All right, so this central angle is 85 degrees. So angle BOA equals 85 degrees. And the cool thing is that not only is that angle, BOA, 85 degrees, but the measure of this arc, this minor arc, is also 85 degrees. So the measure of the central angle that cuts off an arc is the same as the measure of its arc. So the definition there in the book on page 498 is a central angle of a circle is an angle whose vertex is the center of the circle. And then down at the bottom of the page, the degree measure of an arc is the measure of its central angle. So in that case, if we looked at this big angle here, and I'm going to need to draw this radius, not that big of an angle. If I draw OC and we look at the measure of this angle, we know that that's a major arc, right? It's more than 180 degrees. And so let's say that this is 180 plus maybe another 40 degrees. So that's about a 220 degree angle. And it's about a 220 degree arc as well. Now when you have an angle that's greater than 180 degrees, that is called a reflex angle. And so this 220 degree angle is a reflex angle, and all major arcs then have reflex angles. So we've talked before about acute angles, they're less than 90 degrees. Right angles, they equal 90 degrees. Obtuse angles are greater than 90 degrees, but less than 180 degrees. Straight angles are 180 degrees, and now a reflex angle is greater than 180 degrees. A reflex angle is greater than 180 degrees. All right. Also in this lesson, we have something called the arc addition postulate. I'm going to erase this and draw a new circle for us. This is a little bit like the ruler postulate of earlier in the book. Hopefully that means something to you. I know it's been a little while. But I'm going to draw a few radii around this circle. And we'll just name them W, X, Y, Z. I need to go T, U, V, W, X, Y, Z. Okay? Now I'm going to add two of these arcs together. So if I have arc VW, plus arc WX plus arc WX, that equals, so that arc plus this arc WX equals, dun dun dun, you ready? You'll be shocked. It equals arc VX or VWX. I'm just going to write VX, but you could write it the other way and that would be okay. That is what the arc addition postulate says, that when you take two arcs side by side that are adjacent to each other and you add them together, the measure of the new arc is the measure of the two smaller arcs added together. The other, and then we have two theorems in this lesson as well. The first is that in a circle, equal chords have equal arcs. Now, I will ask you this. I know you're watching from home, but hopefully you can answer it anyway. What is a chord? What is a chord? And no, I'm not asking for Mrs. Nolan's definition of a chord. It's a good one, but it's not applicable in geometry class. A chord is a segment whose endpoint through a circle whose endpoints are on the circle. So in this case, I'm going to say VW and YZ are chords of the circle. VW and YZ are chords, not those arcs. I'm not talking about the arcs now. I'm talking about the line segments themselves. Now, our theorem says that equal chords have equal arcs. Let's look at that and see if we can prove how that is true. So we are given, I'm going to abbreviate with a G, that VW equals YZ. And I want to prove that arc V, it's not a V, arc VW equals arc YZ. All right, let's think about this. VW equals YZ. I better mark that. Those two segments are equal to each other. Good. All right, what else do I know about anything in this circle? Well, you probably noticed that I've got a bunch of radii, right? OV, OW, OY, and OZ. What is true about the radii of a circle? Well, they are all equal to each other. So OV equals OW equals OY equals OZ. In this case, what do you notice now about my triangles? Dun, dun, dun. Okay, we have triangle OWV is congruent to triangle OYZ because of side, side, side. Hooray! But I'm trying to prove that my arcs are equal. How am I going to get from the fact that I have congruent triangles to the fact that I have equal arcs? These two angles at O have to be equal to each other. Why is that? That's because corresponding parts of congruent triangles are equal to each other. So I have congruent triangles. These two angles at O correspond to each other, so they are equal to each other. Since those angles are equal, what has to be true about these arcs out here? Well, we come back again to that definition of to the definition of a central angle, and the fact that the arc the degree measure of an arc is equal to the measure of its central angle. And so because these two central angles are equal, therefore arc VW equals arc YZ. And that's the proof for theorem 31. Theorem 32 or 61. 62 is the converse of that. It says in a circle equal arcs have equal chords, and that's one of the that's something that we'll prove in the exercises. But that's enough to get us started now. Okay. I want to quickly go through some of these problems like we would do in class. So sorry. It's almost like class in real life. I want to go through some of these problems like we would do in class and the set ones and see how we do. All right. So turn in your book, if you would, please, to page 500. And you should read the Peanuts comic strip at the top of the page because it's kind of fun. All right. Set 1 problems. Routes to Japan. In planning to sail west from Portugal to the Indies, which was Japan, Columbus based his calculations on the figure below. Points C, J, and P represent China, Japan, and Portugal. Marco Polo claimed that the eastern overland route from Portugal to China, the major arc going from P to C, so look all the way around that major arc, had a measure of 253 degrees. Marco Polo thought that Japan was 30 degrees beyond China, so the measure of arc CJ would be 30 degrees. And you see that little M before the arc there? That's to indicate the measure of the arc. Measure of arc CJ equals 30 degrees. And that's a nice way. That M doesn't mean slope there, it means measure, and it's a nice way to indicate that you're going to give the degree measure of the arc. All right, so number 1, what are angle POJ and JOC called with respect to circle O? They are central angles. Number 2, name the minor arc that corresponds to arc POJ. The minor arc that corresponds to angle POJ is arc JP. And again, when you're writing that, you want to put that arc sign over top of the J and the P. Number 3, name the major or arc that corresponds to reflex angle POJ. So now we're going to look at that same arc, but instead of naming the same 2 radii from O to P and from O to J, but instead of naming that minor arc in between them, we're going to name that major arc all the way around, and that's going to be arc PCJ. Number 4, what's the measure of angle JOC? 30 degrees. That's pretty easy. Number 5, what is the measure of arc PJC? We're going to use the arc addition postulate on this. So we take the measure of the reflex angle that we're given, 253 degrees, and we add that 30 degrees to it to get 283 degrees. Number 6, the measure of PJ is 360 degrees minus that 283 degrees, which is 77 degrees. And so therefore the measure of angle POJ must be 77 degrees as well. Let's skip over to Jupiter's asteroids for right now and see how that goes. Number 14, draw the figure and add to it radii SA, SJ, SB, and the chords AJ and JB. Number 15, why is the measure of arc AJ equal to angle ASJ? And why is the measure of arc JB equal to angle JSB? And that is because the degree measure of an arc is the measure of its central angle. That's kind of the main point of this lesson. Number 15, why is the measure of arc AJ, number 16, why is the measure of arc AJ plus the measure of arc JB equal to the measure of arc AJB? And that is the arc addition postulate. I don't have that up here anymore. All right, number 17, why are triangle ASJ and triangle BSJ congruent? That's because of side, angle, side. So what kind of triangles are they? Well, if we know that they're congruent because of side, angle, side, and we know that that one angle is 60 degrees, they are actually equilateral triangles. I think that you can do the Theorem 62 proof on your own, and that arc illusion, that's kind of a fun one to look at on your own. And then your homework picks up at number 23, and it's 23 to 36. You kind of got an extensive construction there about St. Peter's Square in Rome. I hope you have fun with that and it doesn't stress you too much. And then there are a bunch of proofs at the end of the chapter, and I just gave you that one to do, number 43. You're welcome to do any of the others you want. They'll come up at some point, I'm sure. So that's the end of chapter 12, lesson 3, and I hope you have, I hope you can do your homework more easily now. We'll see you next time.